Uh, Good evening, everyone. My name is Yashpal Mishra, and I'll be presenting my project titled Real-Time Electric Vehicle Dashboard and ADAS Warning System. So, the objective of this project is to simulate how modern electric vehicles collect sensor data, process it using an embedded controller, detect potential hazards through ADAS logic, and display all this information on a real-time dashboard. Although this is a prototype, it is designed by following concepts that are used in actual automotive systems. So, before we begin designing any system, it's important to understand the problem that we are trying to solve. So, modern electric vehicles contain hundreds of sensors that continuously generate huge amounts of data. These sensors monitor speed, battery state of charge, motor temperature, power consumption, torque, wheel speed, and many other parameters. This creates what is called a sensor tsunami because data is arriving continuously from multiple sources at the same time. The second challenge is manual monitoring. Engineers cannot constantly watch every sensor value during testing because there is simply too much information. Important warning signs can easily be missed if someone is trying to observe everything manually. Therefore, we need an intelligent system that automatically processes sensor data, detects dangerous situations, and immediately alerts the driver or engineer. So, first, what is ADAS? ADAS stands for Advanced Driver Assistance Systems. These are intelligent electronic systems designed to assist the driver during driving. Instead of replacing the driver, ADAS helps by continuously monitoring the surroundings and vehicle conditions. The primary goal is to improve safety. ADAS reduces human error by providing real-time warnings before accidents occur. Uh, the examples include forward collision warning, blind spot detection, lane departure warning, automatic emergency braking, and adaptive cruise control. Sorry. In my project, we focus mainly on forward collision warning, blind spot detection, temperature, and speed warnings, which is done using ultrasonic sensors. So, ADAS systems are developed with three main objectives. The first objective is reducing human error because studies show that most road accidents happen due to driver mistakes rather than vehicle failure. The second objective is preventing collisions. By continuously detecting nearby vehicles or obstacles, the system can alert the driver before an accident happens. The third objective is reducing driver fatigue. Drivers often become tired during long journeys. ADAS automates repetitive monitoring tasks while still keeping the driver responsible for making the final decision. So, overall, ADAS improves both safety and driving comfort. So, how we made this project. Let's look at the system architecture. So this slide shows the complete architecture of our project. Everything starts with the sensors. The sensor values are read by the STM32 Blue Pill microcontroller. The STM32 processes the raw sensor inputs, performing calculations and determines whether any warning conditions exist. The process data is then transmitted through UART serial communication. And finally, a Python application receives this data and displays it on a graphical dashboard in real time. So the complete data flow goes like sensors, STM32 Blue Pill, UART, and the Python dashboard. So, since building an actual electric vehicle is not practical, this project uses equivalent components that simulate real automotive hardware. Potentiometers are used instead of wheel speed sensors. By rotating the potentiometer, or in our case, using the sliders, we can simulate changes in speed or throttle position. The STM32 Blue Pill acts as the vehicle control unit, or the VCU, because it performs all processing and decision making. UART communication replaces the automotive CAN bus used in real vehicles. While UART is much simpler, it demonstrates the same concept of transferring sensor data between systems. This allows the project to closely resemble an industrial electric vehicle architecture while remaining affordable and practical. So let's look at some of the modules we used in our project. The software is divided into multiple modules so that each module has a specific responsibility. The EV controller handles standard electric vehicle operations like speed calculations and powertrain management. The ADAS engine continuously analyzes sensor data and determines if any driver warning should be generated. The fault manager monitors the overall health of the system and detects abnormal conditions. The ultrasonic driver interfaces directly with the ultrasonic sensors and measures obstacle distances. Finally, the UART shell manages communication between the STM32 and the Python dashboard. Splitting the software into modules makes the project easier to understand, maintain, and expand in the future. Let's look at our environment setup in phases. So several software tools were used during the development of our project. First, we used the STM32Cube IDE to write and compile embedded C code. Then PixelLab helped simulate the embedded hardware without needing a physical circuit. And Python was used to build the graphical dashboard. Within Python, we used the matplotlib library to create gauges, graphs, and other visual indicators. On the microcontroller side, several peripherals were configured. Timers generated precise timing. The ADC, which is the analog to digital converter, converted analog voltages into digital values. And the UART handles serial communication. GPIO pins connected the sensors to the controller. Uh, in the other phases, the sensor inputs and EV dynamics, raw sensor values cannot be used directly because they are simply voltage readings. The ADC converts these analog voltages into digital numbers. These digital values are then calibrated into meaningful engineering units like speed, throttle position, and battery percentage. The EV dynamics model uses these processed values uh, to estimate important vehicle parameters. For example, it estimates acceleration, vehicle speed, torque, and remaining driving range. This allows the dashboard to display realistic EV information rather than raw sensor readings. Now, let's look at the ultrasonic sensors. This is the main intelligence of the project. Three ultrasonic sensors are used. One sensor is mounted at the front of the vehicle, while two sensors monitor the left and right sides. The front sensor is responsible for forward collision warning. Whenever an object gets too close, the system calculates the distance. If the distance becomes smaller than the safe threshold, a collision warning is triggered. The side sensors implement blind spot detection. If another vehicle or object enters the blind spot region, the driver receives an alert. This demonstrates how ADAS systems continuously monitor the surroundings and help prevent accidents. Now, let's look at how we manage the faults. So, safety systems must also detect failures inside the system itself. Therefore, we implemented a fault management module. Different faults are assigned different bit values inside an 8-bit register. For example, one fault represents excessive motor temperature, another indicates critically low battery state of charge. Additional faults detect collision danger, ultrasonic sensor failure, or UART communication failure. Since each fault occupies a single bit, multiple faults can exist simultaneously without requiring separate variables. So, now the alarm priority logic. Not every warning requires the same level of urgency. Therefore, the system classifies warnings into four priority levels. P0 represents normal operation with no danger. P3 is an advisory warning, such as blind spot detection or excessive speed. P2 represents a moderate warning where collision risk is increasing. P1 is the highest priority and indicates an immediate collision threat. As the danger level increases, the dashboard changes its warning colors from green to blue, then yellow, and finally red. So, this color coding allows the driver to quickly understand the severity of the situation. Um, so, now we come to the last phase of our project, which is the Python dashboard. After processing all sensor data, the results are displayed on a Python dashboard. The dashboard includes a speedometer, battery indicator, estimated driving range, motor temperature, current power consumption, and regenerative braking level. A bird's eye view also displays nearby obstacles detected by the ultrasonic sensors. The dashboard updates continuously as new data arrives through UART. This provides a simple and intuitive interface for monitoring the vehicle status in real time. Here is the demo of how the Python dashboard looks like after the completion. So all simulated sensor values are continuously updated and displayed. The dashboard also shows the current alarm status and EV metrics. Although this project is a prototype, it demonstrates many concepts used in real electric vehicles, including embedded programming, sensor interfacing, serial communication, ADAS decision making, fault management, and real-time visualization. In the future, this project can be expanded by replacing the simulated sensors with actual automotive sensors and implementing CAN bus communication instead of UART, uh, which CAN bus communication is the one used in real electric vehicles. So now let's move on to the STM32Cube IDE code, followed by the Pixum Lab and spare part simulations, and finally the Python dashboard. So now let's see the code which we have written. First, we have defined all the global variables, and then we have read all the sensors using this function, uh, and it reads the analog inputs from the ADC. Uh, this function controls the HCSR04 ultrasonic sensor. This function acts as a simplified electric vehicle model, the EV underscore update function. And then the ADAS underscore update function is where driver assistance logic is implemented. And then let's go to fault check. The fault check function continuously monitors for unsafe operating conditions. Now, here in the print status function, all the processed information is transmitted over UART, and the Python application receives this serial data and converts it into the graphical dashboard. And here is the rest of the code where we have uh, written all the fault logic and decided all the parameters for the GPIO input and output. Now let's move on to the Pixel Lab simulation. So this is the Pixel Lab uh, simulator. The STM32 Blue Pill is running inside Pixel Lab, and we have already loaded the binary file into this virtual microcontroller. Over here in spare parts are all our virtual sensors and sliders and LEDs here. So first we have PA0, PA1, PA2, and PA3, which are the accelerator pedal, brake pedal, battery state of charge, and the motor temperature. Now we have our three HCSR04 ultrasonic sensors, which are the front distance, left distance, and right distance sensors. Here we have our LEDs, which provide immediate hardware feedback. Uh, So let's try the front distance LED. So when the front distance LED goes below a safe threshold, the collision LED lights up. Uh, Here in our left and right distance LEDs, if it goes below safe thresholds, the blind underscore left or the left blind spot LED lights up. And if the right distance is at a dangerous threshold, the right blind spot LED lights up. And you must have noticed the fault LED, which is still lit up. That's because of our state of charge slider, which is at 0 currently, which means it's below the safe threshold of 2%. If we slide it back up, the fault LED turns off, which indicates that there is no fault currently. Now let's open the Python dashboard and see the live simulation. So let's open up the Python dashboard. Here we are. And let's open the spare parts window. So you can see the accelerator pedal is dialed all the way up. Um, and once this acceleration or the speed reaches a dangerous threshold, we will get a warning. So let's reduce that. Um, and the state here's the state of charge. Currently, it's at 79%. And this is the temperature. This is the motor temperature slider. If we increase it all the way up, the speed automatically reduces to 0 because it breaks down at a dangerous temperature and the car completely stops. And the fault LED is also lit up. So let's go back to a normal temperature. This is the front distance slider. Once we get it below 50, uh, we start getting a warning and the alarm goes into advisory mode. And once we go even further below, the car actually collides with the object or vehicle in front, and the speed also goes all the way to 0, and the alarm goes to warning mode. A- and that's also indicated by the fault LED lighting up to yellow. So now let's reduce the left distance or potentiometer, and the left blind spot LED lights up, indicating the danger on the left hand side. And once that goes uh, below a certain threshold, like um, you get no more warnings. The right right hand side works the same way. The right blind spot LED lights up, and yeah. So this is how the project works. Let me show the front distance once more. So yeah, as you can see, it updates in real time, and the Pixel Lab and Python dashboard are connected using a tool called Virtual Serial Port Simulator, the VSP, where we have created two virtual ports, the COM1 and COM2. COM1 is connected to Pixel Lab that sends data to uh, the Python dashboard using COM2. So thank you. This was a very fun project to work on, and hopefully I'll get to work on more exciting projects in the future.